Got a lot of stuff to talk about, um, and we've got an extra load of homework coming up this weekend. In fact, coming up for you guys at 11:50. So let's talk about the homework situation for the weekend. And firstly, you have homework 12 that activates right after lecture today. So that's ready. And it's going to cover stuff that we talk about in today's lecture. And there's going to be a calculation that I do today, figuring out an equilibrium temperature, which is tough. And it's going to require a lot of thinking. And I'm going to record it into a talking PDF and post it, and you'll have some for homework. All right, you'll have that. Plus, I think I put another heat problem in there. In addition, I'm going to set up a mini review homework with a few other things, like stopping distance, boxcars. There'll be a special free fall energy levels problem called the Space Jam Emergency, and it's actually a set of 3 questions in order, starting with easier things and working up to a tougher thing in the context of the Space Jam. And then in the mini review, I'll also put some thermal energy things in there. I think I might also put a heat in there and a thermal equilibrium calculation. I'm not done with homework with the mini review. It's up there. It's going to go active. I have it set to go active tomorrow at 1 p.m. But it's not quite ready yet. So what I want you to do is work hard on that. Just work hard on everything. Read everything. Textbook chapters, additional readings, Twitter, discussions, and especially to the extent that you get stumped on some of the homework, if you do, I want you to blaze up the discussions with questions. If you can do that, it's going to help you. Boy, we have sparse attendance. Boy, this is a bad day to be absent. Whoever's listening to this YouTube and viewing it and you didn't get here for it, boy, oh boy, it's a bad day to be absent. All right, speaking of YouTube, the demonstrations that we did Tuesday are up. I put one of them up, I think Tuesday, and then I got the others up yesterday. Here's David. This is David from the noon lecture. He's the last one. He gets the big picture because he's the last one I uploaded. And then Ashley, Stefan, and Miss Vanessa are also up there as well. Plus lectures, of course. And you can use those. And by the way, for the second demonstration, the one with David from noon lecture, and then the one with Stefan from morning lecture, I added in some extra notation, like a little ticker tape or a chyron at the bottom, specifically about the exchange of angular momentum. All right? Now, you can use that to actually learn and reinforce that idea of interaction through angular momentum exchange. Because it's clear as a bell. The only thing that you can't really see is my right hand doing the right hand rule every time. But I think on David's you can see it. You can actually see my right hand and the thumb of my right hand. And be ready to use right hand rule, even a simple right hand rule question on exam 2. And then let's talk about exam 2. It's everything up to and including today's lecture. So basically chapter 4, 5, and 6. But you know what? It's effectively all the way back to the beginning of the semester because, as I said last time, we're never going to stop talking about F equals ma and velocities and stuff like that. So it's effectively cumulative. But the main topics will be chapters 4, 5, and 6. As before, bring a Raspberry UCF colored Scantron, or excuse me, a raspberry colored UCF Scantron with the Pegasus logo. Bring your iClicker too. Make sure it's and I think almost everybody's registered. Is that right, Darian?
I think so, yeah.
Yeah, I think we got almost everybody registered. But a few of you forgot last time, and those of you that forgot, I'm going to be eyeballing you. I can't remember who it was, but I have a list of you. And just remember to bring your iClicker. Number 2 pencil and a good eraser as always. And a calculator. You may not use your cell phone for any reason. So you have to have a regular calculator. By the way, I have, Caroline's not here. I have Caroline's calculator. I have Abigail's calculator. Anyways, bring your calculator and you'll be good. You may not use a cell phone for any reason. And it'll work just like last time. There'll be, 42 dots and then 3 clicker questions that add up to 8 or maybe 9 if I decide to give you a bonus point. So you'll see when you get it. I don't know. I'll be writing it after today's class. I always write new exams, and they're based on what we do in class. So actually, your contributions, your questions, give me an idea of the level of your understanding and the things that I can interrogate your mind with using this tool called Midterm Exam 2. Another thing I want to mention to you is I'll try to update the clicking summaries in your web courses grades page either this afternoon or maybe tomorrow, okay? So that if you're worried about your grade, and I know maybe a few of you are thinking, oh man, maybe I should do a W because I'm not going to get a passing grade. And I know at this point in the semester, students sometimes worry about that. So I'll try to get that up. And then all you got to do is put your grade together according to the syllabus. I had somebody in web courses discussions ask, I think it was discussions or maybe it was messages, inbox messages, Dr. B, why are the grades disabled? And I said, because web courses Canvas does not know how to calculate our grades. All they do is straight percentages. They don't do any converting, but we convert all our clicker data into 25 points. Web courses cannot do that. We convert all our homework. I don't even know how many homework points we got. We got bunches, and that's going to be converted to 25 points on your semester grade. So now, exam points and bonus points, they go straight into your exam grade. But homework gets converted. Clicking, participation in class gets converted. All right, and web courses doesn't know anything about that. Anyways, use your syllabus and keep an eye on discussions, and I'll let you know in discussions when that stuff is uploaded. Okay, questions about anything that I've covered so far? Okay, let's keep going. We're going to talk more about heat energy today. And we'll finish up Chapter 6. And we'll do a pretty good job with Chapter 6 today. Here's a diagram from page 98. This one is nice because it helps us visualize momentum transfer. What we think is that atoms and molecules on a submicroscopic level that we cannot see exchange momentum with the wall of the container that they're in every time they collide with the wall of the container. So there's some delta P. And because of that, we get a pressure that we can measure. We can't measure the momentum state of individual molecules usually. It's very tricky to do that. But we can get a pressure, and I'm going to show you how the pressure comes out of these momentum exchanges. And also, by the way, kinetic energy, I've already mentioned, is proportional to the average kinetic energy of a gas is proportional to the Kelvin temperature. So let's look at this diagram. There's delta P. So this is a diagram that models or displays a ricochet on the wall of a container. For the red molecule, it bounces off the container. And therefore, the container, it's rigid, and actually it doesn't have to be that rigid, because a balloon will respond to pressure and expand, but it's got enough integrity, enough rigidity to contain the gas, but it's also elastic so it can expand. But anyways, you're going to exchange a little bit of delta P with the wall. Now, every second, there's going to be a number of molecules dropping some delta P. Now, there's a whole range of velocities. Some of them are going to be coming straight in. Some of them are going to be coming in at a slant. Some of them they won't even interact. They're going the opposite direction. They might connect with and interact with the other wall, but not with the wall that you're looking at. But there's going to be some delta P, okay? And the pressure is based on that idea that zillions of little delta P's per second give rise to a force. And the thing is, if you're thinking about this in a container, you really, to account for the total force on the wall, you really have to divide the wall up into, like square centimeters or square meters or something like that, and then count how many delta P's per second you get. All right, so pressure is the amount of force on the wall per unit area. Now, in the metric system, that would be newtons of delta P over delta T, force, per square meter. Okay? And that's known as the Pascal. In the English system, it's pounds per square inch. And pounds per square inch, that's also known as PSI. Another pressure measurement is atmospheres. In other words, not having to do with newtons or square meters, but how much atmospheric pressure is pressing down on us at sea level. Okay, that's the atmosphere. Anyways, newtons per square meter, pounds per square inch rises from momentum interaction. Let me repeat that. Every square meter or square inch of the wall of whatever container you've got gets a certain number of molecules colliding with it every second. All right? So a square inch is going to get fewer collisions per second than a square meter. So the pressure number for PSI is going to be different from the pressure number for newtons per square meter. But it's the same idea. So the pressure is the force per unit area. And it's involved with the momentum states and with the spatial distribution. That's the other thing. Underline the word density of the gas. If you have a highly dense gas or relatively dense gas, that means that every square centimeter, every square meter of your container is going to get a lot more interaction simply because the gas is dense and there's more, But if the gas is sparse, it's very low density, then you're not going to get as many ricochets per second per square meter. All right, so density also enters into it. And that's actually related to something that we'll talk about after the exam, the ideal gas law. And but yeah, every square meter, every square inch of wall gets a certain number of molecules interacting with it. So a little bit of delta P per second, that's a force. And the ratio of the force divided by the unit area in the metric system is newtons per square meter, or this one has a fancy name. It's called the Pascal. Pa is the symbol for it, and it's named after a French scientist named Blaise Pascal, who was a pretty smart guy, mathematician and a scientist as well. And he did a lot of study of fluids, the dynamics of fluids and pressure in fluids. So they named newtons per square meter after him. Okay, I want to give you a clicker question now. It's going to be multiple choice. Get your clicker on. And let me just give you kind of a, let's see if you were listening actually, to what I was just talking about. All right, here's your question. A dense gas, highly concentrated, compared to a sparse gas, very diluted. Read carefully and think. Okay, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ding. Let's take a look at the answers here. Okay, you guys did pretty good. So that means you're listening. And in general, a dense gas is going to produce, you could make a note of this, it'll produce more collisions per square centimeter simply because there's more molecules. That's what density means. Right now, density is, the number of molecules per cubic centimeter. Okay, so every cubic centimeter adjacent to the wall has got a lot of molecules in it, if it's dense. And so therefore, there's going to tend to be more ricochets from that cubic centimeter adjacent to the wall than a cubic centimeter adjacent to the wall for a dilute gas. Okay, dilute gas, there's going to be ricochets. There will be some pressure, but not as much. Molecule per molecule. Now, last comment is, if the wall moves, for instance, like a balloon or a piston in your car's engine, if the wall moves because of pressure, there's some F delta X work being done. And after exam 2, I'll show you a little bit about how that works with the ideal gas law. Because the ideal gas law is an equation of state relating the pressure, the volume, the temperature, and the density of the gas, all in one fairly simple looking equation, but it's tricky to use. But we'll talk about that after the test. Now, in the textbook, I use the concept of e pluribus unum to express this idea of the kinetic theory. In other words, the kinetic theory says you can't really see molecules and atoms in a gas, but if you assume that they obey F equals ma, and if you assume that they have a certain distribution of velocities, spatially distributed, in other words, directions, and speeds distributed, a certain average speed and a low, fewer gas molecules at low speed and relatively few at high speed, and a bunch of them, the majority at a medium average speed. And then if you do a lot of calculus and stuff, you can actually prove that the kinetic energies and the Kelvin temperature are related. And this is boy, it's kind of dark, sorry. I should have made these letters a little bit lighter, sorry. This says average kinetic energy, in parentheses, is equal to 3/2 kT. And I'll show you what kT is in a minute. Now, here's the exchange of momentum. Okay, there's the ideal gas law. Pressure P, volume V, capital, equals N, capital N, times kT. Now, little k is known as Boltzmann's constant. Okay, and capital N is the number of molecules in the gas. And that's related to the density as well. So the exchange of momentum equates or converts to a pressure, and the pressure is the unum. The exchange of momenta are the pluribus. There's zillions of momentum exchanges. And in terms of temperature, there's zillions of kinetic energies, which we can't really track, But if you treat them statistically and using a little bit of calculus, you can figure out these two fairly simple laws. And Boltzmann's constant appears in both. Now, let me give you one more interesting footnote to history about Boltzmann's constant, K, little k. Joules per Kelvin is the unit in the metric system for entropy. E-N-T-R-O-P-Y. Raise your hand if you've ever heard the word entropy. A few of you. Entropy. And a lot of people interpret entropy as disorder. This constant it's pretty mysterious. I mean, nobody knows why temperature and entropy are related, but they do seem to be related by that constant. So here's a picture of Professor von Boltzmann. Interesting guy. He's the one that developed statistical mechanics. In other words, you use the laws of statistics and Newton's laws of motion and a bunch of calculus, and you come up with average kinetic energy, 3/2 kT. You come up with PV equals NKT, the ideal gas law. And that was one of the really big successes that Professor Ludwig Boltzmann was able to claim. So that's a little bit of a blurb about kinetic theory of gases. And it's actually underlying everything that we have done in this chapter. And similar conceptualization, Einstein developed a similar theory for solids back 100 years ago. He was working on that. So there's a lot of stuff, but Boltzmann was the one that first did it for gases and stuff. Okay, I want to recap homework 11, some of the stuff in it. First of all, homework 11, the heat melt heat problem. So better take notes because we're going to go over this carefully. And because I know a lot of people were saying, Dr. B, I'm just not getting it right. I'm forgetting something. Let me double check. All right, so let's go through it. That's good. I like to do this. So for instance, you may have had this very problem. Given 7 grams of ice at 268 Kelvin, heated up to a liquid state at final temperature 276 Kelvin. And then the question is, how much energy does it take? How many calories? All right. And I gave you a little table of data, something like this up here in the upper right. And then I listed the final temperature. And then I said, okay, calculate it like we did on Tuesday. Now let's go through it again. And I'm going to go through the concepts first, and then we'll go through the calculation. So take careful notes. Okay, first thing you have to do is heat the ice up to the melting point. All right? And the formula that you use for that is Q equals mc delta T. All right? That's the heat up equation. Now the mass you use is whatever mass you're given, in this case 7 grams. What is different is the specific heat. Now the problems that we're going to be working on, that you're going to be seeing in the rest of the semester, including Tuesday, maybe, if I give you a problem like this, is there's not going to be any change in the mass. So you're going to have, if you start with 7 grams of ice, you're going to end up with 7 grams of liquid water. Okay, so there's no change about that. But the specific heat is different. So for ice, it's 0.50 calories per gram Kelvin. Also, the delta T's are whatever I tell you that they are. Now, and in this problem, in the homework, everybody had a 5K, because everybody started at 268, and it's 5K up to the melting point. Then you have to melt the ice. All right, now this is a different problem, okay? And you use the idea of latent heat of fusion. Now, at the melting, freezing phase transition, there's a certain amount of energy required to add to the solid phase to break apart those crystalline bonds in the case of ice. Now, you can melt metal too. Metal doesn't usually have crystalline bonds. It has metallic bonds, but same thing, it's got a rigid lattice, and you've got to bust it up. So it's like going... What do people do? I'm thinking about creative destruction. You know, what is it? Oh, okay, let's think about football, okay? If you're a football player, you want to break up the blocking formation of the offense. If you're on defense, you want to break it up. Now, you can't do it by just standing there. You got to come and slam in there. You got to, be able to add some energy to their energy. They're trying to stay together and break apart, and then somebody else can get to the running back. All right, so that's what you're trying to do. Same thing here. You're trying to break apart those crystalline bonds. It takes energy, and that's called the latent heat. Now, gram for gram, it means every gram is a certain number of bonds that have got to be broken. Every bond has a certain number of joules or calories of energy stored in it. And so every gram is a certain number of calories that you need to break apart the crystalline bonds and turn it into a liquid. All right? And that's the latent heat of fusion. Side note, if you're freezing liquid water, 80 calories per gram is what you have to extract from the water. When you make ice cubes in the fridge, it's got to be cold, right? It's got to be colder than the water temperature. Otherwise, it will freeze. So what happens is the water, energy from the water is extracted by the cold surroundings. You're basically heating up the surroundings. And when enough of that is extracted, you get ice cubes. So it works both ways. Second side note. So this would be like A2. A2, second side note. There's a latent heat for vaporization, to go from liquid to vapor. Okay, when you heat up water, you can cause it to boil. Matter of fact, you can, if you have a pot of water on the stove, you can boil it all away, and it goes up into the atmosphere as water vapor. The clouds that you see are formed from water vapor, but a cloud that you see up in the sky is not water vapor. What you see are droplets of little you see little micro droplets of water. The water vapor rises to a certain altitude, and at that altitude, it gets cool enough to condense into little tiny droplets of water. Sometimes they're big enough that they'll condense and fall right down. But usually, if you see a cloud up there, notice that most of the time, the base of the cloud is a certain altitude. It looks kind of flat, almost, not perfectly flat, but fairly flat. And that's the altitude where the water starts to condense. And then if the droplets are really small, the winds aloft will keep them, up there. That's how you get those big, fluffy white clouds. So the latent heat of vaporization is for the phase transition from liquid to gas. And up at a certain level of the atmosphere, from a gas to a liquid to form a cloud. So it's the vaporization, condensation, phase transition. Either way, and it's a pretty big number for water, several hundred calories per gram for water vapor and water liquid. But did you have a question in the back?
Oh, you answered it.
Good. Okay. Anyway, so that's the second side note for that. Now, for this one, it's pretty easy. 7 grams times 80 calories per gram, 560. We'll go over that in just a second. Now, after you melt all of that, then the temperature can start to rise again, because until you melt everything, the joules of energy, the calories of energy from your propane burner, it's not going to change the temperature until it's all liquid. And then it will heat it up. But now you have the same mass, at least in these problems that we're working on, but now you have a different specific heat, 1.00 calories per gram Kelvin, because that's for liquid water. Okay, still H2O, but it's in the liquid state, so it's a little tougher to heat up. It takes a whole calorie to heat up a gram by 1 Kelvin. All right, it's a liquid. Question?
So I get how you got that with liquid water and it's a calorie. How did you get the first one? The first,
0.5?
yeah.
Somebody in the lab measured it. The specific heat is something that you measure in the lab. Okay, and every like a rock, granite is going to have a different specific heat from limestone. And limestone down in South Florida is going to have a different specific heat than limestone over in Italy. And so you just have to measure it. And what is your name again? Aaron? Okay, Aaron. Some substances you can make a theoretical prediction, and get pretty close. But in the end, somebody's got to measure it in the lab. So you look it up on a table, and on the exam, you'll have a table of specific heats. Okay, but you got to know which one to use, and you got to know how to use it. Now this one has a different delta T. So remember, when you're doing this, the heat melt heat, you're going to have different specific heats for the first heating and the second heating, and you might have different delta T's, for the first and the second. It just depends on what your initial and final temperatures are. Okay, in this case, it's 3 Kelvin. And don't forget, in between there, you've got the melting. Right? So the melting. And all of that happens at 273. There's no temperature change. Well, that stuff is melting. And that's why ice water, if you see ice cubes in a glass of ice water, you know what the temperature of the water is. It's going to be 273 Kelvin. All right? But eventually, the room temperature will heat up the water, and it'll heat up the ice, and it'll eventually melt everything. But yeah, it'll all happen at 273. All right, let's do the calculations. First of all, number 2, heat up the ice. Now I removed the concepts from this one, and here's the actual calculation. Q equals MC delta T, 7 grams. Specific heat for ice, 0.50 calories per gram Kelvin. Delta T for this one from 268 up to 273, that's 5 Kelvin. Yeah, so this one works out to 17.5 calories. And notice that grams in the mass, the first parentheses, cancels grams in the denominator of the second parentheses, the specific heat. Also, Kelvin in the temperature, in the delta T, the third parentheses, cancels kelvins in the denominator of the specific heat, the second parentheses, the middle parentheses. So the only thing that's left is calories, and that's good. We're trying to figure out a certain amount of energy in the calorie system. All right, questions about this? Okay, so you guys are going to be experts, I guess. Good. Second, melt the ice. 7 grams, 80, and every gram has to get 80 calories to bust it up from a solid into a liquid. A little bit of creative destruction. So that works out to 560 calories. Yo, Aaron.
Sorry.
It's all right.
So how do you get TF? Or no? Yeah, it's TF. How did you get
LF, you mean?
yeah.
The latent heat of fusion, 80 calories per gram. How did I get that?
Yeah.
In the lab.
So everything that
Yeah, and that's why I give you a table. And even if I wanted you, like I might ask a grad student, okay, derive from first principles using F equals ma, et cetera, derive the latent heat of fusion of water. And he could get close, but it would involve a lot of calculus and a lot of quantum physics and stuff. So most guys, and before there was any quantum theory, back in the 1800s, they just measured it in the lab. So that's what we're going to be doing. All right, third stage. And you can do these calculations in any order you feel like. Like on Tuesday, I did the two heating, and then the third thing I did was the melting. But this is, you have the freedom of doing that whatever way you want to do it. So 7 grams still. And specific heat is different here. 1.00, it's liquid water. And 3 kelvins is my new delta T. All right, so kind of stalls at 273, and your propane burner's got a lot of calories to drop into that sample. 560 calories from your propane stove. And then another 21 once you get everything melted. So the final is 598.5 calories when you add those all up. And so in the homework, you would type in the whole number. And web courses apparently rounds 0.5s up. Okay, so this would be 599 for the final answer. All right. Now let me pause for questions. Yes? Over here, this one right here, in the last one, it's because my final temperature is 276. See up here in the given information? There's my final temperature. So I melt everything, and now I've got 7 grams of liquid water at 273. So now I'm heating liquid water, but only 3 Kelvin. If I give you a different final temperature, like 282 or something like that, then your delta T would be different. So for instance, 282, you'd have a delta T of 9 kelvins. Okay, so that's why this is a brain burner. There's a lot of different things to put together. All right, there's delta Ks or delta Ts to put together, specific heats, and then there's heat of melting. The middle Q. So yeah, and you'll have more practice on homework with it. So good. Now I want a question over here. Good. All right. I want to mention question 13, which apparently gave some students a little bit of a headache. And that is because you were not thinking and reading carefully, because number 8 gave you the strategy for solving question 13. Question 13 is basically asking how many joules of energy in a certain number of food calories. All right, and so basically every food calorie is equal to 1,000 of the little thermal calories, and then each of those is worth 4.184. So a food calorie is the same as 4,184. So if you have 7 food calories, multiply that by 4,184, ding, you have your answer. Question here. Got it? Okay. Yes? You shouldn't have had any round-offs because a single food calorie is going to give you a whole number of joules. A single food calorie is 1,000. So 1,000 times 4.184 is 4,184. So you should have had some multiple of 4184. And if you had a round off, that means you didn't get that factor of 1,000 in there. All right. Okay, let's talk about heat transport. And this is a lovely picture. A guy, fire breather, I guess they call down in New Orleans or something. And what they do is they get some kerosene or something in their mouth, and then they blurp it out, and then they touch it off with the little hand torches off to the side. Now here's another picture. You can see the hand torch really, really well. Matter of fact, that gives us an idea of one of the three modes of heat transport: conduction. This guy has to, that stuff comes out of his mouth as a mist of droplets, but they're not going to spontaneously blaze into flame. He's got to touch that little hand torch to it before it'll detonate, before it'll start on fire. All right? So he's got to have physical, so heat flows into the cooler object. All right? And it raises the temperature of the cooler object. So in this example, the fire breather has to use a torch, because he doesn't want to have it in his mouth on fire. He wants it to be licked. Boy, you'd have to pay me like $17 billion to do that once. I would not want to put kerosene in my mouth or anything like that. Anyways, that's what those guys do. So, counterexample, an insulator. Heat does not flow well from one side of an insulator to another. And you can see an insulator here. It's implicit. Air. Air is a good insulator. Raise your hand if you have a fleece vest or a fleece jacket. See, here in Florida, most people don't have them. But a fleece jacket is this thing which keeps you warm when the temperatures are really cold. And raise your hand if you have a down. Ooh, here's a question. Raise your hand if you have a down comforter or down blanket. Okay, that's more people. Those are really soft and nice, and they're really good insulators to keep you warm from losing your heat because they trap a lot of air. It's not the feathers, it's not the down, it's the trapped air. Okay, so that's an example of an insulator. Another insulator, some metals are actually pretty good insulators. For instance, stainless steel. If you put regular steel into like a campfire, like when you're on a camp out, you put stuff in the fire, I don't know. On a camp out, I always turn into a pyromaniac. If there's a campfire, I always throw stuff in there, see if it'll burn. And one time we were camping, and we found this iron rod from a logging camp, kind of like a piece of rebar. And it was just regular steel, and that thing got really, really hot. We put it in the fire, and we, got that fire really going. And so the end of it was red hot, and we could use it to burn our name into this big log and stuff like that. And, the kind of pyro stuff you do on campouts. But we had to hold that piece of steel, with some gloves or something, because it was a 6 foot long. But it was the end that wasn't in the campfire was still hot. It was conducting heat. But now, if you put a piece of stainless steel in, you can get the tip of it red hot in the fire, but you'd be able to hold the other end away from the campfire with your bare hands. So sometimes a metal or an alloy can be a poor conductor and therefore an insulator. Second mode of heat transport is called convection. Now this picture shows convection. It's basically the bulk motion of a hot blob of substance that rises because it's buoyant. It's usually less dense. So the hot stuff is less dense than the surrounding cooler substance, whatever it happens to be. So this is a hot, I'll bet that most of that fireball that's rising up into the sky is air, but there's just enough flaming kerosene droplets to heat it all up. And so you have this low density blob that's emitting a lot of light and rising up into the sky. And that's the fireball, and it's rising just like a hot air balloon. So it rises because it's less dense. Right? Just like a bubble. If you're in the swimming pool and you blow out some bubbles, they go straight up because the air coming out of your mouth or out of your nose is less dense than the water. So it rises to the top and then it bursts through the top and out to the atmosphere. Okay. Now we mentioned last time the Yellowstone mantle plume. The Yellowstone mantle plume is a good example of convection. And the reason that convection happens is that you have a hot substance surrounded by something that's not a good conductor. Right? So underneath Yellowstone, the rock is relatively poor conductor, or the molten lava underneath Yellowstone is relatively poor conductor. So the mantle plume convects upwards. Same thing with this. This fireball is surrounded by air, and air is not a good conductor. It's an insulator for the most part. And so this fireball rises. It's hot, and it's not losing any energy to the air, or not much. All right? So, a matter of fact, that's what saves this guy's life. He's think about that. I mean, you got that much flame really close to your mouth, but you're not killed by it. It's because air doesn't conduct heat very well. Right? Third, also visible in heat conduction is radiation, electromagnetic radiation. That fireball was losing energy through the medium of electromagnetic radiation, light, infrared, maybe even a little ultraviolet, depending on how hot it was. Momentum and energy are carried by photons of light, any other kind of electromagnetic radiation. For us, a campfire or sunburn from the sun comes to us through ultraviolet, infrared, and visible. But, X-rays, those X-ray photons can transport energy from point A to point B. So if the material absorbs a certain color of light, it'll heat up. Or a certain frequency band, like ultraviolet. So your skin cells absorb ultraviolet. Some of the molecules in your skin absorb ultraviolet fairly well, and it does a harmful chemical reaction as a result of that energy, and that's how you get sunburn stuff. And even the astronauts on the moon require a lot of shielding because there's no atmosphere on the moon. Our atmosphere absorbs X-rays and a lot of ultraviolet that come from the sun, the upper ozone layer. And they protect us, right? But a lot of visible does get through, and a lot of infrared does get through in both directions. But ultraviolet not. So, but up on the moon, the astronauts, boy, they can get fried up there if they don't have good shielding, all right? So those spacesuits have got that's why they're white. White reflects a lot of light. If you see something that's white, it's reflecting all the different colors of visible light. Now, here's the thing about it. The sun deposits about 1,370 joules per second on each square meter of Earth that's facing the sun. So if you could go above the atmosphere, about 100 miles, 200 miles up, you're above, 99.99% of the atmosphere. Every square meter that's facing directly at the sun is getting about 1,370 joules per second. Okay? And so, in other words, out in space, you're getting a lot of joules per second. By the way, students, a side note, a joule per second is also known as a watt. W-A-T-T, named after James Watt. When you pay your energy bill, you're paying for kilowatt hours, like 8 cents per kilowatt hour, right? So those watts, 1 watt is 1 joule per second. So energy going through or energy being used per second is in terms of a watt. So So 1,370 watts. Raise your hand if you have a hair dryer at home, a blow dryer. Bunch of people. Okay. Now the energy rating for a hair dryer, blow dryer, is in the area of 1,370 watts. Okay. So all this, maybe 1,500, maybe 1,000, maybe 2,000, depending on, how big of a hair dryer it is, blow dryer. But anyways, and that's every square meter facing the sun. So if you had a solar cell there that could catch all 1,370 watts, 1 square meter, so about this big, about this tall, you could power a blow dryer from that. Side note, spacecraft and satellites have to prevent solar heat gain, and they use something called reflective mylar. So that shiny stuff you sometimes see, they'll put, they'll in the clean room for a satellite, the last thing they'll do is hood it, put the cladding of mylar to reflect sunlight. But of course, some situations, like, the astronauts, they want to defeat solar heat gain, so they have the gold-coated, very thin layer of gold on their visors. Other places, you want to get as much heat gain as you can from the sun. Solar energy collector, on your roof. So it just depends on what you want to do. All right? And so those are the 3 modes of heat transfer or heat transport. Your brakes on your car, if you have brakes, dissipate kinetic energy as heat. And your brakes can get really, really hot. So they make your brakes from stuff that transports energy away from the contact surface into the rest of your car. So theoretically, every time you hit the brakes, you're heating up your car a little bit. And it's not by a whole lot, but it's still significant, at least for the brake pads. Okay, questions? Okay, let's continue to work on a tough calculation. What we're going to do is mix 2 liquids in thermal contact, and they're going to be at 2 different temperatures. And because of that, they're going to be out of equilibrium. But because energy will be transported from the hot to the cold, they'll gradually, you got a hot substance up here, and you got a cooler substance down here, and eventually they'll exchange energy and eventually bounce out. And at the same temperature, they'll stop trading excess energy from one to the other. They'll just be at equilibrium. So here's our example. We're going to use 2 blobs of 2 imaginary substances labeled H and S. All right? And each substance has different specific heat. And we're going to say that the blob of substance H has a temperature initially of 333 Kelvin. And that substance S is a little bit cooler, so I made it blue. It's at 288. All right? And we're going to assume that there's no phase transition, so it's 2 liquids. Okay, and they stay liquids. All right? Now, gram for gram, they heat up differently. And so I just made up 2 round numbers here. These are imaginary hypothetical substances. So don't try to look these up in a table of specific heats or anything. Anyways, so a nice round number, 1.2 calories per gram Kelvin for H. So that's relatively easy to heat up and cool down. If we extract energy, it'll cool down. It only takes 1.2 calories per gram to bring things down by a Kelvin. And by the same token, the specific heat over here, another nice round number of hypothetical substance S, 1.4 calories per gram Kelvin, right? So this one's a little tougher to heat up. 1.4 instead of 1.2. All right, now, which one of these is going to cool off? Let me ask you this. It's not a clicker question, but think. Which one's going to cool off? Raise your hand if you know. Steph. Substance H is going to cool off because that's the hot one. So make a note. Energy is going to flow from H into S. And so whatever energy H loses, S is going to gain. So when H loses, 10 calories, S absorbs 10 calories. But the problem is that if you lose 10 from H and gain 10 in S, you're going to have different temperature changes. Delta T's are going to be different. And this is where it gets a little tricky. So let's work this out carefully. All right. The other thing is, each substance also has a different mass. So even if something's easy to heat up, if you have a lot of it, it's still not going to change the temperature very much. All right, so you got to factor that in as well. So I made up a couple nice round numbers for this one. 40 grams for substance H and a little bit more for substance S. So this is like putting a droplet. You know what this is like? And on homework, you're going to have a coffee cup and a few drops of cream that you're going to put in and see what the temperature changes. That's what it's like. Okay, so we have M subscript H, 40 grams for the hot stuff, the yellow stuff. And then the cooler stuff is 75 grams. Okay? You know what that means? Since the mass of S is bigger than the mass of H, and since the specific heat of S is bigger than the specific heat of H, that means that when they exchange energy, H is going to cool down more than S warms up. They're not going to be the same size, and whatever delta T happens is going to be bigger for substance H than it is for substance S. Okay? So, but here's the main idea here, right? That whatever one in this, we're assuming that it's in like a styrofoam container, so they're not losing energy to the environment. It's all insulated. Okay, but they exchange energy within themselves. Okay, but whatever energy goes from substance H, it's going to be absorbed joule for joule, calorie for calorie in substance S. So for instance, for substance H, if I say that substance H loses 200 calories, then that's going to be MC delta T for subscript H, or for substance H. So what we have to do is figure out, we use the Q equals MC delta T equation, but now we're figuring out what delta T is. Okay? And delta T is going to be, my initial temperature minus my new temperature. Okay? And 200 calories is going to dip the temperature down. And 200 calories gained by substance S is going to heat up substance S. And so we have to figure out delta T subscript S. Right? And we're going to do that on the document camera. So let's go to the document camera for the last 15 minutes of class. And I'm going to pause. Let me get my cursor back here. Come on, baby. Cursor, where are you at? There we are.
Or is it on you?
It's in my pocket. It's not filled out yet. You're Aaron, right?
Yeah. Cause I
Hold on a second.
okay. I tried to go to your office hours on Monday, and then I guess you were at lunch or something. 'Cause-
On Wednesday.
oh, you have Wednesday office hours, not Monday office hours. Okay. And then
Yeah,
yesterday I had practice.
Monday I didn't come up to campus because
Okay. And then I was gonna come during one of your Tuesday because I was sick on Tuesday, and I was gonna come during one of your other classes, and it was just a whole.
I was wondering
mess.
where you were on Tuesday.
Yeah, I was not feeling great. It was a bad day, and then I had a math test after that.
Do you have an ASSA advisor or something?
Yes, I do.
Tell her to send me that. They've been sending me electronic forms for other athletes.
Okay.
You're an athlete, right?
Yeah, rowing.
Okay, Rowan. Yep. Tell her to send me that, and I'll be able to do it. And then I don't mind doing this, but I just forgot to do it.
Okay, honestly, it doesn't have to be, perfect. It's just I really need to turn it in.
Yeah, that's what she
Today.
Yeah, if possible.
The one at 4 is
All right. Let me pause the podcast.
Okay, thank you.
Gotta be able to.
Probably, I'm not 100%.
Okay. There's the strategy. Narrow the temperature gap to 0.
I just wanted to double check, make sure.